Thank you, everyone. My talk is based on this our publication this year, and neutrino flow in leptophilic U1 models. I'm going to talk on neutron and modification in specific this one. Why all that will be. So for general background, I talk about dark matter candidate is not there in the standard model. So even if there's observational evidence, as we know, galaxy rotation, cosmic cluster, etc. And also BSM model suggests different dark matter candidates, seems dark photons, etc. And also I can talk about, but no dark matter candidate is observed up to now. And the probe is on from different directions, like direct, indirect, and collider experiments. So to ascertain what is the nature of the dark matter candidate. So some direct detection experiments, if you list to LUX, Xenon 1T, and CDMS experiment. So neutrino flow is a critical component in dark matter direct detection. Neutrino flow, when I talk about, like, it is the background to the dark matter signal. So in dark matter physics, the impact of the neutrino BSM physics is important. So that is done through this idea of neutrino flow. So again, then direct detection, if we talk in detail, so there is one component is dark matter signal. Okay, so how that is getting generated? The dark matter particles hit the nucleus of the detector material, and dark matter nucleon to dark matter nucleon scattering happens, and then also it can hit the electrons, and the nucleus or the electron, uh, they recoil with energy dictated by this scattering process. And if that is and the recoil energy, if that is above the threshold of the respective detector, so then you have a possible observation. And what is neutrino background? The same processes can happen even through neutrinos. Neutrinos also scatter with nucleon and electrons. So coherent elastic neutrino nucleus scattering, CE nu NS. Okay, this N is missing. So then neutrino flow idea. In a cross section versus mass of the dark matter plane, this cross section is dark matter nucleon cross section in general. So in plane, where there we can draw a boundary, where the neutrino background remains indistinguishable from the possible dark matter signal. Even if you see a dark matter signal with that cross section, you won't be able to distinguish between two ideas, like if it is coming from a neutrino scatter or a dark matter scattering. So that region is called neutrino flow. That flow, and below cross sections below that flow. So significant neutrino flow enhancement. Now motivation to look at neutrino flow, if it enhanced, can lead to fake positive DM signal events, and also without the DM signal present, dark matter experiments we can use them to probe neutrino flux induced events. Once experiments become sensitive to the neutrino flow, as we'll say, like Xenon 1T is already coming closer to the some part of the neutrino flow. So here it's a probe of neutrino sector beyond standard model physics. So the earlier attempts towards this direction as effective models were studied, and also B minus U1, B minus L model was studied. But two new dimensions for our work is the model independent framework doesn't include like all constraints and rigors, because model to model constraints vary a lot for neutrino site. A lot of new constraints which work on one model doesn't work on another model. So for tree level couplings, modifications are expected, but even we look for them for a loop level coupling. So we look for a U1 models and the general Lagrangian of an U1 model, and all L mu minus LE, LE minus L tau, and L mu minus L tau models, or U1 model, and their Lagrangian is known. And then loop mediated neutrino neutrino scattering process that happens through G prime gamma mixing through this loop. So this process, and then due to this process, the rate of change is through this ratio. Okay, when this ratio, and we look for like if there are 5% increment there, like mu each L mu minus E L mu minus Le model and Le minus L tau model. So 5% increase we try to, we see that the all the regions with 5% increase, more than 5% increase is within the um, within the already disallowed region or from other constraint. But the case is slightly different, and it's better from our perspective when you look at L mu minus L tau model. So there we look at like there the constraints are completely like constraints are less severe, and so that a lot of points with these are the points with having more than 5% increase, and these are the points here we look at like where the increase in the this cross section, neutrino scattering cross section is more than 50%. So this is for more than 50%. So even and why the difference between these different kind of U1 models? This is due to the beam dump experiments, electron beam dump. So these constraints, while either we talk about these, and also the earlier this constant on the model, there we talk include all beam dump experiment, Xenon works in a coherent. A lot of experiments when included coming from this paper. And constraints from Texono, especially for this region, you see like there this region is ruled out, and also this extra region that is ruled out. So those constraints, this region is ruled out for other models for Texono because it's a neutrino electron scattering. Also E-beam electron beam dump probes that exclude this region for other two models. So those that accounts for the different seen as modifications in versus this model versus this model. So from there, now maximal enhancement we chose from this yellow dot, the benchmark point, G prime mass 19 MeV and gauge coupling this. And with that, we we reproduce from other older work already, like the what is the amount of the neutrino flux coming from solar, atmospheric, and diffuse supernova neutrinos. Solar neutrino contributions are way more, and these are not that much, and that results in a profile like neutrino event, number of recoil event nucleus event rate. So this rate comes down to this number, and there also we see like there's an enhancement due to the and this profile mimics somehow the way neutrino flux, majorly due to the neutrino flux ID, and there the enhancement is due to the cross-sectional enhancement. This is cross-section part, and this is probability when neutrino coming from solar neutrino is coming, they have their oscillations, and this is the flux amplitude, and this we take 1, and this is for exposure, which is we take 1 year and 1 ton. So this calculation, with that we get like neutrino rate, and then we go back to neutrino flow. For neutrino flow, we have to understand. So there we have calculated neutrino event rate. So now neutrino flow, we have to find out dark matter event rate. Okay. So the definition is there. The cross section on the neutrino flow will be set such that like cross section. So for each one neutrino event due to the scattering, if 2.3 dark matter signal events or more we can observe, then we see then we will call that to be an exact with 90% confidence level that comes from a dark matter signal, and that is not a background, may or may not be background. So below that everything remains within the neutrino flow. So that is the defining like boundary of the neutrino flow. So then dark matter nucleus scattering event rate we found out, we find out from this formula, and exposure and this volume integral is calculated using these ideas already, and these all things we all known numbers, and from there we from the both side we equal, like these are dark matter number event and these are neutrino number of events, and their ratio should be 2.3 by 1. So for one neutrino event, 2.3 dark matter event. So that translates to a cross section limit is like this. So inverse of the exposure was there in this part, and that comes this side, and rest of the part is like this. So then this is the cross section formula, and when you use that formula properly, we get neutrino flow, enhanced neutrino flow. So and if we increase, if we magnify it, we can see like this is the neutrino flow due to the U1 model, and this is the neutrino flow due to the standard model, and up to the 10 GB here, and here it's a from 5 to 30 GB. We can see like that, and this is for a xenon germanium based experiments, and this is for xenon based experiments, and they are when and we can look at like the different experimental now current and future experimental probes, and those are also here. You can see here, you can see like the all other experiments, if a super CTM CGP is only probing into this region, like the already, I mean, it not probing like in the future experiment, like and they are, if it is a normal like standard model neutrino flow, so it's not getting to reach going to reach there. But if it's enhanced neutrino flow, it may see some events, but that may not be due to dark matter signal, because if we calculate neutrino flow properly, we'll see like the neutrino flow is already enhanced, and this enhancement, and it 110 GB DMS enhancement of the neutrino flow is by a factor of 2.7. So upcoming CTMS enhancement can see, and also the Xenon 1NT experiment can probe in here the enhancement is around this region is 1.8. And then I summarize, like if a dark matter direct detection is being discussed, a possible modification, background modification must be discussed, and U1 model has a unique feature that significantly enhance this cross section even through a loop mediated effect. So that leads to an elevated neutrino flow. So elevated neutrino flow, the scope of the future experiment hitting the floor gets increased, so leaving no room for a dark matter direct detection. So, but there can be other models, like along with the search of DM candidates which can evade the strict direct detection bound. Alternately, there can be like models where dark matter is present, but also you can decrease the neutrino flow, so that can be searched for.